Okay, the second question is the simplest possible linear regression model where there is only one regressor and the regressor is binary. So x is binary, it takes 1 or 0. So we are going to simplify everything. And here I am going to take two different approaches. First, I will just take this question as a separate question, standalone question without any previous knowledge. And the second approach I'm going to do here is I will borrow the general theorem that we did in question 1. So let's do this. So the first question, we would like to show this. Pretty straightforward. To do that, what we are going to calculate these two separately, right? This guy y, replace y with the linearity assumption. And excuse me, let me erase this for now. And then, so conditional expectation is linear in this argument. So first, we have alpha 0. Alpha 0 is constant, so it's not affected by expectation, plus expectation beta 0 xi given xi equals to 0, plus expectation ui given xi 0. Okay, so it is alpha 0 still, and in the second term, beta 0 is constant, so you can move beta 0 out of the expectation, and then this becomes 0. So in the end, it will be 0. And the final term is also 0 using this assumption. So it is 0. So simply, it is alpha. Okay. Similarly, you can show that this equals, so I will skip the first line, same thing, alpha 0, beta 0, expectation xi given xi equals to 1, plus ui given xi equals to 1. Okay, and again, this is 0, and now this is 1, because x is 1. Then, in the end, it is alpha 0 plus beta 0. That means, how can I add a page? Let's add a page, see. So that means we get expectation y given x 0 is alpha 0, y given x equals to 1 is alpha 0 plus beta 0. So then, pretty simple, alpha is already proven, beta is their difference. Right? Pretty simple. If you take the difference, like, subtract the above one from the bottom, then you will get this result. Pretty straightforward. It's also very intuitive. When x changes from 0 to 1, it's increased by 1 unit, and then the expected change in y is beta 0. That is the definition of the slope. So we get what we want. Okay? So it is pretty simple. Okay, that was a proof that does not utilize the general theorem. We did not use the general theorem here. Let me erase all the things. Alternative proof is, using, so first check the conditions for the general theorem, and then use the result, theorem result. It means, so the first step is you check exogeneity and full rank assumption, because linearity assumption is, I will write it down, linearity assumption is automatic, it's the same thing. So we are borrowing the the result from question 1. And if you additionally check these two conditions, because it already satisfied, then you can claim the result following these assumptions. The result is alpha 0, beta 0 equals inverse this. So, right, this is using the result we already proved, and then what you have to do is checking the assumptions and then translate the result, the conclusion, into our setup, okay? So, checking those conditions are actually question B and C. Let me do that, okay? Erase everything. Okay, so first, exogeneity condition. It's pretty simple. We wanted to show expectation of xi ui is 0. By the way, here x is confusing, but I'm saying like xi should be interpreted as 1n lowercase x, because we have two parameters. One is intercept and the other is scalar x. But our general theorem used this notation, upper letter x, which includes all the regressors as a vector, right? So if you take this notation, then this means two equations. Okay? And we have to show this. We have to show this. And what we have is, already we have these two conditions. It looks pretty easy to show this result using our conditions, given conditions from our question. Okay, then expectation of unconditional expectation of u equals expectation of u given xi xi equals 0 times probability x equals 0 plus ui given xi equals to 1 times probability x equals to 1. Okay, it doesn't matter what these guys are. We already have this equals to 0, this equals to excuse me, there was a typo. It's not probability, I meant expectation of u, right? So anyhow, both are 0. So we already proved this part. Okay, that was proven. Now let me erase those things, and let's see how we can do the other part. We now want to show that this is 0. Okay, we don't need 0 here. Okay, we would like to show that there are many different ways, but you may use the similar formula xi ui given xi equals to 1 times probability xi equals to 1 plus expectation xi ui given xi equals to 0 times probability xi equals to 0. Okay, here then, first, when x is 0, this will be 0, so this part is automatically 0 by construction. It does not need any assumption, right? So already x is fixed at 0, so x times u is always 0 no matter what u is. And then this part is by construction again, because x is already 1, it will be this, right? X is already 1. So, and you know this is assumed to be 0 using this one, right? This assumption implies this is 0. So this is 0, this is 0, so all is 0. The second assumption is already verified. So in this way, we are proving the exogeneity assumption, right? In this case, as you can see, this is not a smart way, right? Because already question 2 is pretty simple. So checking the exogeneity assumption is already like longer than proving alpha and beta. Like answering the question A without using the previous results. But it is just a practice. So let's see. The next, we have to show full rank assumption. Okay. Again, we are going to use like uppercase X as a vector. Okay. And then we need to show that xi transpose is invertible. We have to show this, right? It's overkill, but let's do exercise. And it is easy to, excuse me, I will erase here. Easy to see that the 2x2 matrix can be written in this way. We just need to show this 2x2 matrix is invertible. Okay? For this matrix to be invertible, its determinant should be 0. And the determinant equals AD minus BC. Right? This guy. So you just need to calculate this and this, which is simple. Let's check. Expectation of xi square is expectation of xi square given when x is 1 times probability x is 1 plus expectation xi square when x is 0 probability x is 0. Then it is clear this is obviously 0, right? So you only have this, but in this case it is 1, right? It is not 0, but it is definitely it is 1 when x is 1, its square is also 1. So the expectation x squared equals probability x equals to 1. Okay, then now let's calculate expectation of x. You can follow the same steps and you will get the same result. It is interesting. The expectation of x squared and expectation of x are the same. That's because x is 1 or 0, like 1 or 0. So if you square them, same. They don't change. They are a square, or like no matter how many times you multiply them, they are basically the same thing. Okay, and then let's go back to the determinant. I will erase here. Then let's think about the determinant. So here I will use notation P, which is simply probability of 1. So I showed you the squared expectation is P minus simple expectation P, but it's squared. So that is what we get. And it shouldn't be 0. What is the condition? When it becomes 0? Obviously, you can rewrite this in this way. So if P is 0 or P is 1, then this determinant becomes 0. So we would like to avoid them. Okay, we have to, we cannot allow P equals to be 0 or 1. That is also intuitive. Let me intuitively explain that. If P is 0, then it is not invertible. The identification fails because we do not observe no observations of 1, excuse me. So probability of x equals to 1 is 0. Then we never observe x equals to 1. That means all observations have simply 0. There is no variation. It is just a constant. You cannot identify that. It's a multicollinearity with the constant. Same thing, if P was 1, that means there is all x equals to 1. Probability of x equals to 1 is 100%. So again, it is constant. which is multicollinear with the intercept. So we cannot identify the coefficient. There is no variation in x in those cases. Okay. Then finally, it is not a question, not in the question, but you could answer question A using those conditions, right? So because you have now, you show that linearity assumption is given, and you showed exogeneity assumption, and you already showed full rank assumption, right? So under those three assumptions, you prove that we know the general result. This, right? We can now claim this equality under those assumptions, right? And let's do that. Expectation xi x prime was, remember, this guy, and remember it was 1 p p p. P was probability of, so P is probability x equals to 1, okay? And then we need its inverse, okay? Its inverse is P minus P squared in the denominator, and I learned it in high school still. This is, I believe this is the inverse, right? 2 by 2 matrix inverse. I'm not sure if it's right. And now let's calculate the second part. Expectation of x times, I'm sorry about that. So the second part is a vector, even I was confused, including those two guys, right? Expectation of y and expectation x, y. How can we do that? We are going to rewrite them. So expectation of y will be decomposed as before, I did it earlier, times probability x equals to 1 plus expectation y given x equals to 0 times probability x equals to 0, right? This is what we did. But here, instead of the probability, you can use p, right? Using this notation. And this part is 1 minus p, okay? Similarly, I will calculate xi times yi. Probability xi yi given xi equals to 1 times p plus expectation xi yi given xi equals to 0 times 1 minus p. But here, this is 0 because x is 0, so we can ignore the second part. So we have, and also this part can be simplified to expectation of y given x equals to 1 because x is 1. Okay, then from here it's pretty simple, simple algebra. You need to then what we just saw is we saw that alpha 0 beta 0 can be written as xi transpose inverse expectation xi yi, and we saw that it's like p squared in the denominator 1, like p1 minus p times here expectation. Let me write bu1 as expectation y given x equals to 1 and bu0 as expectation y given xi equals to 0. Then here we get bu1 p plus bu0 1 minus p, and here bu1 p. This is what you have to calculate. Then I'm not confident. I believe you can do that, right? So what I wanted to show you here is the solution that I showed you earlier is the smartest way. That's it.